Welcome everyone. Next we have bitwise operators, but before learning about bitwise operators, we need to understand the binary representation of integers in Python. These bitwise operators, they basically work only with integers. Now we know that everything is stored in computer in binary form, right? Which is nothing but zeros and ones, which we call as bits. These bitwise operators, they work at bit level of integers. That's why the name bitwise operators. So it's essential that we understand the binary representation of integers in Python. The first point we need to understand about binary representation of integers in Python is that Python uses 2's complement binary representation of integers. In fact, it is worth noting that most of the other popular programming languages like Java, C, C++, they also use 2's complement binary representation. Without getting into too much details of this 2's complement representation, one important information we need to understand is that in this representation, the leftmost bit is used as sign bit, which means the leftmost bit is 1 for negative integers and 0 for non-negative integers. Non-negative includes 0 and all positive integers as well, right? So let's take this example of 5-bit binary number. You might have learned about this conversion from binary to decimal in your school math courses. So generally what happens is from left to right, we give weights to these binary positions starting from 2 power 0, 2 power 1, 2 square, 2 cube, and 2 power 4. That's how we generally give the weights, right? So we give weights in this way. Now, if you want to convert this binary to decimal number, so what we have to do is we have to multiply each bit value with this weight and add all the terms. So it will be 0 into 2 power 0, which is 0, plus 1 into 2 power 1, which is 2 power 1, plus 1 into 2 square, which will be 2 square, plus 0 into 2 cube, right? So it will be 0 plus 1 into 2 power 4, which will be 2 power 4. Now, as you can see here, the bits which are 0 can be ignored because the terms will be anyway 0. So we can simply say that it is nothing but the sum of weights at positions where bits are 1, which is 2 power 1 plus 2 square plus 2 power 4. So that's the general representation of binary numbers we used in our high school maths. But when it comes to 2's complement binary representation, the leftmost bit is used as sign bit, which means that this position will have a negative weight. So if you see, the first position has 2 power 0, next 2 power 1, 2 square, 2 cube, and the last position will be instead of 2 power 4, it will be minus 2 power 4. Now, what does this mean having leftmost bit as 1 and why will it give negative integers? Let's see this logically. If we understand the logic behind it, right, you don't need to memorize it. Then things will become much easier to learn. Now, if you keep this leftmost bit aside for a while, if you see only these 4 positive positions, what is the maximum number possible? It is when all these positions have ones, right? So then if you add these weights, it will be 2 cube plus 2 power 2 plus 2 power 1 plus 2 power 0, which will be 15. And the minimum will be when all these are zeros. It will give 0, right? So if you take these 4 positive positions, they will give values from 0 to 15, right? Now, if this leftmost bit is 1, this will give you weight of minus 2 power 4, which is minus 16, right? So this minus 16 outweighs even the maximum positive number possible with these rightmost 4 bits. So that is why if the first bit is 1, it will definitely give us a negative number. And if it is 0, the negative position will have 0 weight. And so it will only result in all the non-negative integers. Now, if we try to evaluate this number in 2's complement binary representation, so this is how we do it, right? 0 into 2 power 0 and 1 into 2 power 1 plus 1 into 2 square plus 0 into 2 cube. And this last position has negative weight, so it will be minus 1 into 2 power 4. If you sum them up, you will get minus 10. If the leftmost position had been 0 instead of 1, we would get positive integer, right? So let's try to find its value. So it will be 0 into 2 power 0, 1 into 2 power 1, 1 into 2 square, and 0 into 2 cube, and this leftmost position is 0 now, so it will be minus 0 into 2 power 4, which will give you a value of 6. Now let's see how we can convert a decimal number to a binary number. To do that, we use something called division by 2 method. You might have studied about this in your school, but I'll just give you a quick recap. All right. Let's say we have an integer value 12, right? Now, in order to convert this 12 to a binary number, what we can do is we will repeatedly divide the number with 2 and keep track of reminders. So basically we have 12 here. Now 2 divides 12 completely 6 times and remainder will be 0. Now 2 threes are 6 and remainder is 0. Now 2 ones are 2 and remainder will be 1 in this case. And finally, what will be the remainder when we divide 1 with 2? 2 zeros are 0 and 1 will be the remainder. And we will stop here. So you'll have to continuously divide with 2 till you reach this 0. Now we take these reminders from bottom to top to get the binary representation for 12. So it will be 1100, right? So this is how we generally find out binary representation of a decimal number. But we know that Python uses 2's complement binary representation, right? Which means there has to be a sign bit on the leftmost side. So what we do is we take this 1100 and add a sign bit 0 on the left. So the 2's complement binary representation of this integer 12 will be 01100. Now you can also cross verify this by converting it back to decimal by doing 0 into 2 power 0 plus 0 into 2 power 1 plus 1 into 2 square plus 1 into 2 cube, and last bit will have negative 8, and so it will be minus 0 into 2 power 4. If you add these terms, you will get the value 12. All right. Now, one interesting thing we have to observe here is that so 01100, this is the 2's complement binary representation. Now, if you add more zeros on the left, even now, if you try to find out the value of this binary number, it will still be 12. So when you take a positive integer, even if you extend by adding more zeros on the left, the value will still be the same. So integer 12 can be represented by 01100, or it can also be represented by this 0001100, and it can even be represented with more bits as well by adding more zeros on the left, right? But what we get here by doing this division by 2 method is the minimum number of bits we need to represent integer 12 in 2's complement binary representation. And also one interesting fact about Python is that there is no fixed size for integers in Python. If you take other programming languages like Java, integers have fixed size of 32 bits. But in Python, there is no fixed size for integers. And finding the exact size of integers in Python is complicated. So what we can do when we want to evaluate bitwise operations is that we can use this minimum size representation, which we get by using division by 2 method, or we can even extend by adding bits on the left. In the next video, when we discuss about different bitwise operators, we'll see an example to understand why and how we can extend the bits. All right. Now let's see one more example to understand how to convert to 2's complement binary representation. So here we have integer 121. Now if you try to divide with 2 continuously, 2 60s are 120, remainder will be 1. Now 2 30s are 60, remainder will be 0. 2 15s are 30, remainder will be 0, and so on. And finally you go till 2 zeros are 0 and remainder will be 1. Now, if you take these reminders from bottom to top, the binary representation will be 11110001, which is this one. And in 2's complement binary representation, we need to have a sign bit. So because this is a positive integer, we will add a sign bit 0. So the 2's complement representation of 121 is 011110001. And remember, this is the minimum number of bits we require to represent 121. If we want, we can even add more zeros on the left. So we have seen how we can find the binary representation of positive integers, but how to find the representation for negative integers. Now in case of positive integer 12, we simply added a sign bit 0, right? So we got 0, 1, 1, 0, 0. But in case of minus 12, we can't simply add a sign bit 1 on the left to get its 2's complement representation. In fact, if you try to evaluate this 1, 1, 1, 0, 0, you will see that the value will be minus 4 and not minus 12. So finding the 2's complement binary representation of negative integers is not very straightforward. So what we do is we make use of one interesting property of 2's complement representation. Now let's see what that property is. So the next point we need to understand is 2's complement of an integer will negate the integer. For example, 2's complement of 12 gives minus 12 and vice versa, which means 2's complement of minus 12 will give you 12. So how to find this 2's complement? So 2's complement of a number n is 1's complement of a number plus 1. And this 1's complement is nothing but the first bitwise operator, which is bitwise not. And bitwise not or 1's complement is very simple. It's just inversion of bits. For example, if you take integer 12, we found its binary representation, right, just now. Now, if you take 1's complement, all you have to do is convert 0 to 1 and 1 to 0. So you will have 1 0 0 1 1. So this is the 1's complement of 12. Now 2's complement of 12 is nothing but 1's complement of 12 plus 1. Let's try to find it out. So 1's complement of 12 is 1 0 0 1 1. All right. And binary representation of 1 will be 0 1. All right. Now we need to perform bitwise binary addition for these two values. Now, just like how we do normal addition with decimal numbers, even in case of binary numbers, we'll have something called sum and carry. So when you add two bits 0 and 0, the value will be 0. And if you add a bit 1 with bit 0, the value will be 1. Now if you add bits 1 plus 1, the value will be 1 0. Just like when we add decimal numbers, let's say we get a sum 15, what we do? We keep the value 5 and we take 1 as carry to the left position, right? So similarly, what we do in case of 1 0 is that we take value 0 and we send this carry 1 to the left position. Now let's try to add these two binary numbers. So here we have 1 and 1. So the value will be 1 0. So we take 0 here and we send carry here. Now here we have 1 plus 1 plus 0, right? 1 plus 1 plus 0. So 1 plus 1 will give you 1 0 and plus 0 will not add anything. So the value will be 1 0, right? So what we do again here is we take the value 0 here and we send the carry here. Now in this position, we add 1 plus 0, the value will be 1 and now there is no carry, right? Now here we have simply 0, we take the 0 here. Here we have 1, we simply take 1 here. So the value will be 10100. Now if you convert this binary number to decimal by doing 0 into 2 power 0 plus 1 in plus 0 into 2 power 1 plus 1 into 2 square plus 0 into 2 cube and minus 1 into 2 power 4, we will see that we get a value minus 12. So we have seen that by doing 2's complement of 12, we got a binary representation for minus 12, right? So in general, finding binary representation of negative integers is not as straightforward as positive integers. So in order to find the binary representation of a negative integer, what we can do is we can take the binary representation of positive integer and then find its 2's complement, just like what we have done here. We have computed the binary representation of plus 12 and then we found the 2's complement of it, which gave the binary representation of minus 12. Now let me show you a small demonstration. So I've created a Python file called bitwiseoperators.py in this operators folder. All right. So here I'm creating two variables a and b with values 12 and minus 12. Now in Python, there is a function called bin, which will take any integer and it will give binary representation. So here I'm trying to print bin of A and bin of B. Now if you try to run this program, we can see that the output is 0B 1100 for plus 12 and minus 0B 1100 for minus 12. But this is not exactly the 2's complement binary representation, right? So we have seen for 12, the 2's complement representation is 01100, and for minus 12, it is 10100. But generally speaking, we are not used to 2's complement representation, right? In general, we are used to this kind of representation without sign bit, right? 1100. So Python's bin method gives this representation so that it is much easier for us to read. So 1100 is 12. So 0p1100 indicates plus 12 and minus 0 b1100 indicates minus 12. But this is not how the integers are actually stored. They are stored in 2's complement representation, which we have seen before. So whenever we want to evaluate any expression involving bitwise operators, we should not use this kind of representation. We should be using 2's complement representation to perform these operations. In the next tutorial, we're going to see some examples, then it will be much more clear to you. Alright, now that we understood the binary representation of integers in Python, let's discuss about bitwise operators in the next video.